All right, ladies and gentlemen, I just wanted to touch base and provide you a little bit more, sort of just follow up on what we should have seen last week and give you a little help on what we're looking at this week, okay? One of the first things we saw was a free body diagram, and a free body diagram is really just a drawing, and it's an outlet for us to illustrate the different forces acting on an object. Much like our drawings in the past, the shape of the object, not super important right now, um, but it is important just to be able to visualize what forces are acting in which directions, which might be canceling each other out, and being able to move forward. As far as what a force is, it's a push or a pull. Okay, whether that is directly in contact or there's other different types of forces that might act from a distance, like gravity. But any sort of push or pull can be considered a force. We've got all sorts of different forces that we'll talk about. Friction is going to oppose the movement of an object, excuse me. Tension might come from a rope if you're using a pulley, or you see them a lot on bridges. Okay, normal force is going to come back a little bit when we start to talk about friction, but it is the force put on an object from whatever surface it's resting on. We have air resistance that comes into play when we start having larger, just like we were talking about projectiles in the last unit. Larger surface area is going to make air resistance, increasing importance. We have applied forces that are, sort of a blanket term for anything that's not covered in any of these other categories. Generally, going to be a result of some sort of person or machine applying a force to a system. We can have spring forces, which change a little bit as they are compressed and stretched out. So we've got all these different types of forces. Let's put them into, some sort of relationship moving into our laws of motion. Our first law is all about this thing called inertia. Okay, the law itself says an object in motion is going to stay in motion. Something at rest is going to stay at rest unless our forces become unbalanced and there's this outside force acting upon it. Okay, inertia we find is a function of mass. So we get into our first relationship here. We talk about weight versus mass, and that equation can be illustrated below here. Weight can also be, you can also use F sub g. Okay, the force of gravity is the same as an object's weight. And that is my mass times my gravity. Remember, gravity is acting downwards, so it's a negative 9.81 meters per second squared. Getting into our second law, it's saying that an object's acceleration is going to be dependent on its mass and the forces that are acting on it, excuse me. So we see just a different variation of the same equation. We have our net force, F sub net, equals mass times acceleration. Getting into our third law, it is stating for every action, there's an equal and opposite reaction. We have these things called action-reaction pairs, which are just forces that oppose each other and essentially cancel each other out. Okay, so going back through these, we have, I want to draw some attention to the simulation we were working with last week. I'm in my friction tab because that's where the real world things have friction. And this is a good tab to sort of show all three of our different laws. So in our first one, the one thing I don't like about the simulation here is that it's not showing any forces going up and down. We can imagine that it's going to have some weight going down. We see our mass here is 50 kilograms. I could multiply that by 9.81 and find that I would have, that's going to take me to somewhere around 500 newtons, just roughly 10 times 50. And that's going to be acting down. Now, this box is not going anywhere. So that would tell me that there's some force acting back on it. But at the same time, I'm talking about my first law here. It is not moving left or right. An object is at rest. It's going to tend to want to stay at rest. Now, that's not to say that that's not overcomable. Okay, so moving into our second law here, I could continue to apply force. I can see now that I've overrode, its friction, and I can see that this speed is changing. My speed is changing. That means that I have some sort of acceleration that is present. What is it exactly? I'm not 100% sure right now, but I can see that my speed is changing, so I know that it's there. And then getting into our action-reaction pairs, I can sort of go back to what I saw here a minute ago. I like to keep my values there. If I were to be able to illustrate that, I would see an action-reaction pair going up and down. I would have the force of gravity along with the normal force. I can see it here. I have my applied force to the right, my frictional force to the left. Until I increase my force to a certain amount to overcome that friction force, that would be considered an action-reaction pair. Again, these forces are balancing each other out. The box is not moving. There's zero acceleration. My forces are balanced. F net would equal 0. Okay. Something else that we will talk about, our last equation has to do with friction. I hope to get some more screencast examples both on Newton's second law and our friction formula. And in those, I'm going to take a look at these last couple of practice problems on slide 12 and 13. Okay, and I will touch on friction a little bit more, just because I'm getting a little on the long side here. I'll touch on friction more with those problems. So, again, shoot me any questions on Schoology. I hope you guys are doing well, and I'll see you later.